In case you missed the notification, go to that website real quick that has both the slides available and a link to download Haskell. I'm a particularly big fan, especially when you're learning something as crazy as Haskell, of actually having it out as you go along. Just because, for me at least, that tactile experience makes it a lot better. But everything you need to is from right there. So, before I begin though, I want to talk a little bit about what is Haskell. So I'm going to ask you guys a couple of quick questions. How many of you have programmed in functional languages before? Alright, how many of you programmed in some of the more pure functional languages, Lisp, Haskell, like that? Alright, so you're all pretty well versed in that. How many of you have taken PLC? Okay. So a bit of the beginning portion is dedicated to talking about the peculiarities of functional programming languages. If this is a bit, if you guys have already seen it, just tell me to go a little bit faster. But before we start, I like doing this, bringing up the big description that they put on the website. Haskell is a computer programming language, obviously. In particular, it's polymorphically, statically typed, lazy and purely functional, and it's quite different from most other programming languages. So what do all of these big fancy PLC reminiscent words mean? The first thing we're going to talk about is the polymorphically static typing. So Haskell, you don't ever have to care about types if you're doing really simple things. That being said, under the hood, it is very statically typed, and things are going to be expecting the right types. So for example, you can see we've got the int type, we've got the bool type, we've got the char type. What's worth noting though is you can actually make type declarations on your functions, and I'll go into this a little bit later, but what's cool to notice is that the types can also be variable, sort of like your generics in Java or C++. So if you have a type declaration on your function like that, it can be a character, it can be an int, it can be a boolean, as long as the other end is also a character, an integer, or a boolean. Another thing is Haskell is lazy. So things are not evaluated when they're bound. So take this expression, for example. We have, what this says is, take the first 5 elements out of the list this. So what is the list this? Well, that is actually a list of 1 to infinity. And just to prove it, I'm going to actually go over here and do it. If I pull up terminal. So like 1 ... it'll just keep going forever. But if I do take 5, we get 5 elements out of that. That was the particular demonstration that wowed me the most about Haskell. Things are evaluated when they're executed. So if you want to define an infinite list, you can define an infinite list. It's just make sure you're actually taking out a limited set of things out of that. On top of that, it's purely functional. So in your imperative languages, like your OO languages or your procedural languages, you're going to execute statements and have state change. In a functional language, you're not going to execute statements, you're going to evaluate expressions and have no states. It's worth noting that in Haskell, they have this concept of a monad, which is where you pretend to have state. But again, that's a Haskellism. Basically, it's a way of chaining operations together. But at the end of the day, you have no state in Haskell. You're not going to have your standard OO or procedural variables that exist beyond the program. So now that we talked a little bit about what Haskell says it is, I want to talk a little bit about what a functional language is. Functional languages have higher order functions, purity, lazy execution, and recursion, obviously. So with a higher order function, you pass in functions as parameters. You guys are all pretty familiar with functional languages, it looks, so this should make sense to everybody. You say filter with an odd function, you get a list, and you get out odds. With a square, you just filter out all the squares. And those are just functions that take in an integer and return a boolean. Talk a little bit more about purity. A lot of the languages I was exposed to in PLC weren't strictly pure, so I think it's worth going into a little bit. Pure means there's no side effects. There is no state, and a function, given the same input, will always return the same output. So that function filter EQs with that list, anytime you execute it, there is no way to make it do anything different. It will always do that same thing. And like I said, Haskell does have monads, and they're used to simulate the side effects within the system that you might have. For example, input-output is technically done through a monad, so you can see things that come in and come out chained together. And we're going to see that in a little bit. We're going to see some very basic monads within the scope of the project. I already told you what lazy means. And then finally, recursion. Same as recursion in any other paradigm, but it's worth noting that in a functional language, oftentimes the only way to iterate over a loop is the only way to iterate over a loop is through recursion. So you're not really going to use a for loop per se. You're going to actually iterate over the list using a recursive scheme where you wait until the end of the list and then you say I'm done. With that being said, are there any questions on what functional programming is? I spent a little bit less time than I was expecting to because everybody seems to be familiar with it, but if you have any questions, go ahead and ask me now. The reason I focused a lot on that at the beginning was because when I was learning Haskell, it was really important for me to actually get those functional programming ideas and concepts down really hardcore, because there really is a very strict adherence to those principles within Haskell, with a focus on making a nice developer experience. So, getting started in Haskell. A couple of quick comments on the Haskell environment. Haskell, if you install the GHCI, if you install the GHC version of Haskell, which stands for the Glasgow Haskell compiler, you're going to get three main executables. You get your GHC, which is your compiler. You get GHCI, which is an interactive REPL session. And then finally run GHC. What's really cool about Haskell is you can run Haskell files through an interpreter like Python. So run GHC just runs through the file, runs through it in an interpreted manner. And when you're happy with that, you can actually go ahead, compile, and run it as a compiled language. And there is a performance boost because it does all the compiler optimizations it can do and works out the byte code, the bits and bytes so that they're optimized as well as the computer can handle it. Finally, there's GHCI, which behaves like IRB would, which is where you can plug and play with a lot of things. You can load external files in, but if you just want to run a file at the top level without having to import it and run it specifically, you just use run GHC. In Haskell, you have an entry point called the main function. Exactly like C and C++, you define your main function. It's not like Ruby or Python where if it's at the top level, it gets run. And the basic output function is called print. So, real quick, we have our hello world function. It says main is the function that is print hello world, where hello world is a parameter of print. Pretty straightforward stuff, right? Makes sense? If I wanted to complicate it a little bit more, we could use the do notation. Technically, this converts main into a monad, but you don't really need to worry about that too much right now. Just know if you want multiple things to happen in your main function, you say do, and then do the whole list of things. All of the code that I have sampled up on the screen right now is available in the GitHub repo if you want to take a look at it and run it yourself. Like I said before, I'm really a fan of that tactile experience where you touch and play with the code yourself. Also, I want to tease Jeff Lindsay just a little bit. Jeff, I am showing people how to print. Jeff ran this TechTalk 4 years ago and did not show people how to print. So at least I beat him in that one regard.
Better than a former president. Yeah.
Cool. Make sense to everybody? So, now that we've taken a look at our first Haskell program, we'll look a little bit about what functions are in Haskell, because it's really important to understand what's going on with functions because it's a functional language. Haskell has some really silly function notation. So dollar signs and dots do not do what dollar signs and dots do in other languages. The dollar sign can be referred to as the function applicator, and the dot is the function composition operator. So all three of these print statements actually do the same exact thing, and are really basically the same thing. It's just they're going to work a little differently. So if we were to do this in the traditional functional programming sense, you have your parentheses and everything's done in a parenthesis. You call f on g of 1. I have my functions up there. F of x is just add 1, g of x is just add 2. So let's say I didn't want to have these end to parentheses. We can use something called the applicator function. And what that does is it'll say everything after that, evaluate it, and then pass it into print. So if I didn't want to use those parentheses around everything after print, I could use the dollar sign. And a notation that I would like to see right there is f of g of 1. If you wanted to, you can expand that out and also do dollar sign f, dollar sign g 1. From there, you can also use the function composition notation. This is very similar to the function composition you'd see, in a strict math class. So f.g means execute G, then pass in the result to f to execute with f on one. So when we do that, we actually get a whole new function, and that function can then be applied to the parameters that you'd be expecting for G. Does this make sense to everyone? Yes?
Which one of these would be the convention? Like, what would you typically see for something in here?
It's very contextual. It depends on what you're doing. You're going to see the $sign a lot more just because people use that for the top-level functions. You're going to see the $sign a lot more in general. So that's probably more the convention. But in an instance like this is probably the most sane notation. So whatever's sane, but you're going to see the $sign more often. Answer. Yes?
Can you omit the parentheses from the first one, and will it, assume that it'll take
so you can't technically omit the parentheses necessarily. You actually, if you wanted to write it, you'd have to write it like that. The way Haskell reads this is, if there were no parentheses here, it would say print is a you would be passing in these three parameters to the print function, because the way it evaluates. So to ensure that the order of operations happen as you wanted, you'd actually have to say explicitly those are the order of operations you want.
That'll only happen because it knows that print can take multiple arguments, right?
It actually doesn't know that print can only take multiple arguments. It makes no... Haskell doesn't say print can only take one argument, therefore I should be expecting these all to be one argument.
Okay.
It says print, you can have all the crap over here, do with it what you want. And then the Haskell typing system will say, oh, by the way, print's a function that only expects one parameter, I don't want this. So if you did this without it, you'd actually get a type error.
Okay.
Makes sense? Yeah. Yes?
The white space, is it important?
The white space isn't important, yes. So that requires that the white space be done correctly. There are other syntactical things like the while statement requires that you be tabbed in right. And Haskell will yell at you if your white space is incorrect.
Also the white space between the $signs and the F's and the D's?
I believe that is. I'd have to double check, but I believe that is, yes. Go ahead. In particular, did my answer make sense to you?
Yeah.
Okay, cool. Alright. So now that we started talking about the functional stuff a little bit, I want to talk a little bit about currying. Who remembers currying from their PLC class? Alright. So if you don't remember, okay. Sometimes they go over it, sometimes they don't. So I'll give you the top level spiel real quick. Currying is where you partially fill out the parameters on a function, and then it creates a new function that expects fewer parameters. Best way to explain this real quick is with an example. So I have a function called double us, which takes in two parameters x and y. And let's say for whatever reason, I don't feel like filling in one of the parameters. I don't feel like filling in that y parameter, that x parameter. So I can say double us is 10. Double us is 10. And what this returns is a function that expects one parameter, which we then evaluate down here. So what's happening from the top to the bottom, we have our double us function declared. We go through, say, double curry is a function, being the function double us with the first parameter 10, expecting a second parameter. So when you run and evaluate this, you get double us 1 and 2, or a double curry number 2. You can see that there. Does this sort of make sense to everyone? Yes?
What's the part with the double colons and the types?
Excellent. So this is technically called a type declaration. I'll explain that in just a minute. It's just if anybody was a bit familiar, I wanted to offer this to them. And I'll explain these type declarations in particular in a minute. So, real quick, what this is a type declaration saying this function does this. And I'll go and explain what it does real quick in a second. There's one more thing I have to explain before I get there. The other thing I have to explain is that functions technically can't have more than one parameter. And a function with two parameters is technically a function that returns a function and accepts a parameter, and all sorts of things going on and on and on. This is where Haskell really started to lose me when I was first starting to learn it. And this is where Haskell's purity and adherence to lambda calculus principles, like you were asking before, really shows through. So, to look back at that type declaration, what this reads to us in normal human speak is double us is something. And that something is a function that accepts an integer, that accepts a second integer, that returns an integer. So that x maps to the integer right there, that y maps to the integer right there, and that integer maps to what we have all over here. And we can see that if we start breaking it down a little bit more. This is the output of a GHCI session. The :T notation in GHCI stands for output the type of whatever it is I have. So, for example, the type of double us is A to A to A, where A is a number. And what we have here is it's a function that takes in an integer, takes in a number, puts it to another number, that returns another number. So when we curry that down to double us 10, what that is that's just a function that accepts a number and returns a number, because we've taken off one of those parameters. And then finally, when we call double us on everything, it's just a number. Does that make a little bit more sense out of the whole currying thing? Because currying is is a really important principle to understand in Haskell, because a lot of the notation that they're going to wind up using, and a lot of things, confusing, weird things that they're going to do, is going to come from currying. Also, for me, when I was learning it, one of the most important ways to understand the typing system for me was understanding what currying was, how it worked at the use case level, what was the use case of currying, and then once I understood what currying was, I was able to understand, oh, functions aren't technically multiple parameters. They're just functions to functions to functions, which accept parameters all the way up the chain. Especially, did that answer your questions a little bit more?
Yeah, I think so.
Yeah, and that's one of the most important things I want to try and explain out when I'm talking about Haskell. Haskell is a language that does what it wants to do, doesn't care if it really makes sense at first, but then the more you get into it, the more it makes sense out of everything. And when I was talking to my friend Mike, he's a big functional programming language enthusiast, he said, Haskell, you're just explaining all the silly things it does and why they make sense. And I said, yeah, basically. Haskell does a lot of silly things, but they actually make sense. So to talk a little bit more about the typing system, Haskell is strictly typed under the hood, and you don't ever have to see those types. For example, in a lot of the early examples I was showing you, I didn't declare any types, didn't care, they didn't need to be there. As long as I was right, Haskell didn't mind. But you can explicitly write out the types on a function. If we're going to talk a little bit about the conventions of Haskell, generally speaking, if you're writing a reusable library or code that you're going to ship, you usually declare the types on a function. That way you get a lot more. It's almost compile time information, but it's actually, it'll wind up being compile time information if you compile it, runtime information if you're using the interactive shell. But it gets you all those benefits you get from a typing system in like C or C++. You get a compile time where it says something really weird is going on here that you wouldn't get in necessarily, say, a Ruby or a Python without going through a weird stack trace. It'll say very explicitly, the types are wrong, you should fix this. So what helps me is if I'm having a problem in just a quick little script I'm writing, I'll add the types and then I'll make everything like a little bit more sense. So for example, I have a function here, and that function prints out x. So it's expecting an integer, and it's going to return an integer, where show x is the method in Haskell that takes something and converts it into a string. Technically in Haskell, strings are just char arrays, like C-style strings, but you can think of them as strings because you can represent them as this way. So there are a couple of typing errors here. First being, it actually does not return an integer. The second being, it doesn't accept an integer when we throw it in here. So when I try to run this, I'll get this crazy stack trace. So the first thing says, we expected an integer, but we actually got a char list. In the first argument of f, namely 1, 2, 3, in the expression f1, 2, 3, in the equation for main f1, 2, 3. So when I'm going through writing my Haskell, doing something, I can say really simply, oh, that means I have a type error there. Why am I using that function that way? What's going on wrong here? And it's a really good tool for trying to evaluate that out pretty well. Does that make sense to everyone? Is the typing system starting to make a little bit more sense, everything coming together? Haskell's an environment where you start to have to see the whole picture before everything starts to make sense. Any questions on the typing system? Okay. And finally, one of the last core concept to understand about Haskell is are lists. If anybody's done anything with a functional language before, you know lists are like the cornerstone of everything. And you'll get your traditional list functions that you'll have, map, filter, reduce, the standard functional things. Has anybody not seen map, filter, reduce before? In any language, whatever paradigm, doesn't matter. Ruby in particular loves to steal map, filter, reduce from the functional paradigms and put it into its own language environment. So let's take a look at a couple of lists that I have declared. The first is a simple list. And a simple list is just brackets, commas, and stuff. I showed you the infinite list scheme before, but you can actually bound those ranges. So if I have a range list, I just say 1.100 within the list brackets. Very similar to like the range function in Python or the dot notation in Ruby. You can also set the delimiter. You can only do arithmetic sequences with this notation, so you can only say 2 to 4 all the way up to 100. You can't do you can't fine-grain control the delta through the comma notation. But real easy to just produce a list of even integers I want. You can also use list comprehensions, and list comprehensions are one of my favorite things about Haskell. So for example, I want all of the perfect squares from, what are you doing, Nick?
That's cool.
You can do all the perfect squares from the roots 1 to 5. So what this says is, give me the list of x squared where x is all of the elements in the list 1 to 5. This, you'll note, has a lot of strong pulls from set theory and math. So this is pretty closely resembles, as much as you can, the set theory, set style of notation you'd see in math. So that's where list comprehensions come from. I personally think they make a little bit more sense in Haskell than they do in Python, but I'm not going to get in the way of anybody loving Python. And if you want to see real quick, you can see the perfect squares. One little bit of notation I've added here is the plus operator. So the plus operator can be thought of as a concatenate operator. To be technically correct, it's actually a monadic operator that you use and you define in your monads. But at least for lists, it just means concatenate. And since technically strings are just char lists, if I want to concatenate strings, I use the list concatenate operator. So I get my list of perfect squares, I convert that into a string or a char list, and then I concatenate these two char lists into one, and then I finally print that out. Does this make sense to everybody? Yes?
Are ranges a separate class from list as they are in Ruby, or is it just another syntax?
It's just another syntax. This will evaluate out to the technical type list. Cool. Make sense? Yes, sir.
Why isn't the plus at the beginning of the statement?
Good question. I should have answered this beforehand. There are two types of operators. There are prefix operators in Haskell, and there are infix operators. Your standard plus, minus, divide, and concatenate are infix operators. Everything else is a prefix operator. And the function applicator technically converts it into an infix function. Oh no, it doesn't. Sorry. There's this other operator, the backtick operator, will convert a prefix function into an infix one. I'll show you that real quick. So if we're usually looking, the modulus function in Haskell is mod. So mod 5.2 is 1. Most people don't like having, if I tried that, it should work. Yeah, there's no such thing as the mod operator. But if I want to write something a little bit more mathy, something that's an infix rather than prefix, what I can do is I can go 5 backtick mod 2, and then that makes it into an infix operator. I only know how to do that with parameters that accept 2 functions. I don't know how it works with 3. Yes?
Is there like some special reason those are all infix versus, a lot of lists doing things prefix?
So Haskell has the second driving motivator over purity is making it syntactically nice. So things that you always expect to be infix, most, like, very specifically the basic mathematical operators, they'll do infix, so you don't have to try and wrap your head around, like, the list style add or whatever. So it really is to make the development experience a lot easier.
All right, so it's to prevent all the parentheses sitting at the end.
It's
of
to
the list.
prevent all parentheses
When
or
you're doing
the
most-
absent parentheses that you don't know what are going on. So yeah, it's just to make it nicer for you as a developer. Very good question. Thank you, thank you, thank you. Right. Cool. And the next thing I want to talk about, which ties in very strictly with list, is something called pattern matching. So function headers can have the expected object already declared. So it maps the most fitting portion, and just let me show you real quick what's actually going on. So I have a function, mymap, where we're expecting a function that takes A to B and returns a list. So it takes in a function and a list and returns a second list. There's already a map function written within the Haskell standard libs. I just wanted to write it out for myself so you guys could see how pretty straightforward it is. So the way I would write a map function in Haskell, thinking in a Haskell manner, is recursively. So what that means is I have two cases, my general case and my base case. So my base case for what mapping a function over a list is mapping a function over an empty list, and that just returns an empty list. So my base case actually is written out in this pattern matching scheme. And for me, I really love that because it makes it a lot easier to follow, and you can write your recursive functions just like this and not have to worry about it. And the reason it's tied so specifically with lists is recursion, and this notation right here is how we quote-unquote iterate over a list. So does anybody have a guess what that is from their functional programming language experience at all?
Cons, if you're talking in list terms.
Exactly, yeah. So what that means is, because we're expecting a list, this is the head of the list and the tail of the list, where the head is the first node and the tail is the remaining bits. So what this function says in plain English, given my map is a function that expects a function and a list with the head being x, the tail being xs, I then apply the function to the head of the list and concatenate with the remainder of the list being thrown through the mymap function. And that's the recursive call here. So, in particular, the things I really like most, the pattern matching, that notation for lists. And this sort of even goes into a bit of logic programming almost, with that I declare the list is a head and a tail sort of notation. You can also start doing all sorts of other crazy things. Like if you want the first two elements of the list, you can say, you can be like y, x, xs. There are also notations to get out the tail. I think there's a notation to get the tail element out of the list. I'm not familiar with that. But this is a really easy way to iterate over a list, just recursively. And one of the reasons why I prefer Haskell over something like Lisp is because it makes it so simple to do that recursion with the base case. So you're actually dealing with lists in a sane, safe manner. And just for an example, I'm going to print out my map with a function and a list. Does anybody know what this is?
Add 3.
What's the technical name for this? We talked about it. This is currying, actually. So I partially filled out the plus operator already. I said, all right, I'm going to want to add 3 to something. I don't know what it is. So I'll just write plus 3, and plus 3 is a function that accepts a parameter and automatically adds 3 to it. So this is where we start seeing that currying notation used really heavily, is when we start getting into the list operations. So I say, I have a function that I want to do to everything. Instead of writing out a function, add 3, accepts one parameter, add 3, I can just use the built-in plus sign and know, because we have currying built into Haskell, I can do it automatically. Yes?
Are there anything like, I guess the word is guards, like there are in Erlang, for if you were doing recursion with numbers? Like if you wanted to do a Fibonacci sequence, so you'd have everything for 0 and everything greater than 1, but how would you deal with negative numbers?
So guards. There are things called guards in Haskell, actually. And the way that looks is you actually have a pipeline. I'll try, actually, right after this presentation, I'll try and write that out, a Fibonacci using the guards. So the way it works is you have, you'd write a function, and you'd write a bunch of guards, and it probably similar to, I'm not familiar with Erlang, but you'd say, Boolean condition, if true, do this, Boolean condition, do this, otherwise, and there's an otherwise operator, otherwise, default down. And that's called, those are called guards in Haskell as well, and you do have them. They're not used, so you can't use them at the pattern matching for function declarations level, but you can use them inside of the function actual declaration. Yeah, good question, I like that a lot. Other questions? No, cool. So, questions in general, like I said, I really wanted to provide a high-level overview of what Haskell is and get you at least your feet wet and to start how to think in a Haskell manner. A lot of your knowledge is going to come from thinking how should I do this Haskell-y, and then what do I do to get to that point. If I had any recommendations, the Project Euler things, a lot of them can be written really easily and really well in Haskell, and I do a lot of them that way. When you start getting into things that require like performance and stuff and things to not take forever, like if you start having to calculate primes, it starts to screw up a little bit with big numbers because functional languages stereotypically aren't good at doing things in a performant manner. But it's really nice, and it's really fun for me to write them out because there are a lot of really mathy questions to write them in a language with very strong math backing. Any questions on this? Any questions about Haskell? I'm not done yet, but yes.
So I may have missed this, but you mentioned monads more than once.
Yeah.
Did you ever get to a point where you actually explained them well?
No, I did not get to a point where I explained them well. The reason I did that is, personally, I'm not even 100% comfortable with explaining monads. That's not why I did that. Jeff Lindsay also did not explain monads, so I feel a bit more okay with that. So monads require a very hardcore understanding of the typing system and how functions aren't really functions within Haskell. The online guides in particular, Learn You a Haskell is really good at explaining what a monad is. But a monad, in the most simple terms, is how do you chain operations together. When you're learning Haskell, the only times you're ever going to use a monad are with input-output and with, technically lists are monads with that concatenate operator, but fortunately, and I think this is the really cool point about Haskell, you don't need to understand the underpinnings of monads to at least start to begin doing things with lists and I/O. So there's an example in my repo called Hello World Under 2, where you get to see how input works, and that's a very heavy, that's a heavy-duty monad. You don't need to understand monads to use it though, and that's sort of why I didn't want to get into it. One, because I can't explain it too well, and B, because it's not 100% critical to understanding Haskell, at least at the beginning and intermediate levels. I will answer a question. Oh, sorry, yes?
When you use the dollar signs for evaluating functions, are they always processed right to left?
Yeah, so if I go back, silly Haskell notation. So the way this works, like this one in here, it says print that stuff, F that stuff. G1 gives you a result. So I'm effing the results over there. You're going to have to bleep that out. And then I'm printing out the results of my stuff. Any questions? I'm going to answer a question that Doreen asked me about my presentation. Why in the world would you use Haskell? First answer is it's fun. I really love coding in this way. For me in particular, I love math, I love programming. It's a really cool way to intersect those two parts of your brain into one, because you get to apply a more creative, more creative approach, a more artistic approach to math, and at the same time you get to apply a more mathematical approach to programming. So it's sort of like art and math merged into one. Yes?
It gives you suggestions when you mess up.
Exactly. It's really nice. It says, did you mean this? Did you mean that? The other thing is there are a lot of places they're using it in the real world. One of them I know is they are using it in a semiconductor design lab where they're designing semiconductors out. And they have a formal language built on top of Haskell where they try and understand semiconductors and they perform analyses on them. There are also frameworks out there you can use. A couple of people there's a web platform written in Haskell, so you can write your blog in Haskell. don't do that. But you could if you wanted to. But for me in particular, it's just for things that are very mathematical oriented, where you want to solve in a mathematical way, you can do it with Haskell, and it's really fun to do. Yes? Questions? Great question. Like I said, sources, Haskell Wiki, really, really good. The other thing, Learn You a Haskell, free ebook on the internet. There's lots of pretty elephants in there. It's really, really cool. It does a nice job of explaining and teaches you functional programming as you go along. Yes?
Y Combinator?
Y Combinator?
I heard it's hard because of recursive types or something. Can you explain that?
No. So the Y Combinator, I'm not 100% familiar with, to be honest. That's one of my weak points. If you want to write out a Y Combinator, there are tutorials online. Danjo did one, if you want to ask Danjo how his experience went. History, I took a Haskell class taught by Professor Schreiner in the CS department with Dan Joseph, the vice president, one of the vice presidents from last year. Loved the heck out of it. We stayed up many an hour working on the assignments he had for us. Well, if that's it, I'm going to go, and thank you guys for coming. I'm going to try and write that Fibonacci sequence out real quick with guards, just so you guys can take a look at it, but I'm going to call the presentation done. All right. Thank you.